Ladies and gentlemen, welcome to section 7.8, Applications of Logarithms. We're going to jump into our first two formulas, and it is the growth and decay formula, which is given by y equals a times e, which is always a constant, as Euler's number is that irrational number, k is a constant of time, and k actually tells us whether it is growth or decay. If it is positive, it's going to be growth. And what do you think if it is negative? It would be decay. So K is going to tell us if it's growth or decay. And then we also have our constant T time. So what do these problems look like? We have a radioactive isotope decays with time in 9 years. I bet that's interesting. Just half the mass of a 20-gram sample of an isotope remains. This period of time is called the half-life of an isotope. Find the constant K for the asymptote when T is given in years. First thing we have to do is to find all our missing variables. So here A, what are we starting with? This one it's kind of tough to tell, but just half of the mass of a 20-gram sample. So we're going to start with 20 grams. What is our time period that we're looking at? We're looking at 9 years. And what is our final amount? Here the final amount, it says in 9 years, just half of the mass. So half of the mass, half of what? Half of 10, or half of 20 is 10. So my y is going to be 10. So now I'm going to plug all my variables in here. So I have 10 equals 20. And then my Euler's number, my constant here, is just going to be e. That's an e, right? We have that number in our calculator. We do not know our k because we are looking for a k. And then times 9, those are exponents. Let's clean this thing up. We want to get e by itself, correct? So we're going to divide by 20 on both sides to get 0.5 equals e to the 9k. Now, how do we deal with this e here? We have to take the natural log of both sides. So we take the natural log of both sides. And so the natural log of 0.5 is negative 0.6931. And that gives me, I bring the k down because of the power property. The natural log of e, please remember, turns into 1. So I'm going to simplify some more here. I'm going to rewrite it as negative 0.6931 equals 9k. How can we get k by itself? We have to divide both sides by 9. So k equals negative 0.0770. We have our constant k for the isotope. Now it says it is decaying, so should this be negative? Yes, it should be negative, so we have our right k. Next, we have a paleontologist examining the bones of prehistoric animal estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. And for carbon-14, we're going to use that right there. So we have y equals a and then e to the negative 0.00012 t. Now what is our a going to be? Our a is just going to be when it was alive. So our a is going to stay a, but now what's our final amount? Now they contain 2% as much as they did when they were alive. So our y is going to be 0.02 a, because that's how much is left. 0.02 as much as when they were alive. So let's go ahead and plug it in. We have 0.02a, that's going to equal a e to the negative 0.00012, and t, because we do not know what our t is. First things first, we have to take care of that a because we want to get e by itself. We can divide both sides by a. So I'm going to divide both sides by a. When I do that, I come up with 0.02 equals e to the negative 0.00012 t. Now what do we have to do to both sides? We have to take the natural log of both sides. When we take the natural log of both sides, we get 0.02 equals the natural log of e to the negative 0.00012 t. This now comes down, the exponent comes down because of the power property of log, so it's negative 0.00012t. That equals, or actually times, the natural log of e, And then that equals the natural log of 0.02t is a negative 3.912. Now, what's the natural log of e turn into? That turns into just a 1. So we will be left with a negative 0.00012t. That equals a negative 3.912. Dividing by this, because it is attached through multiplication. Decimals are numbers too, so we divide by this decimal. We get, when we divide, 32,600. What is 32,600? That is years, right? This is years. So 32,600 years ago the animal did live. Now we are asked if prior research to the animal being around 20,000 years old, how much carbon-14 should be in the animal. Again, we are going to use this right here. So we have y, let me try that again. We have y equals a e, and that is to the negative 0.00012 t. Now we have 20,000. What is 20,000 going to be? That is going to be our t. So y equals now a e to the negative 0.00012 times 20,000. A lot of numbers going on right here. Now if we multiply everything out, we have y equals a e to the negative 2.4. From here, what is this a? This a is going to be one whole when the animal was alive. So what if we just let that be 1, because that was one whole? We are looking for the percent of carbon that is now in the animal. So if we just let that be 1, we have y equals e to the negative 2.4. So now once we have here, we can just plug e to the negative 2.4 in our calculator and get 0.09, or how much carbon is left in the animal? 9% of the carbon. Moving to now, in 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion. We are asked to determine the value of k in China's relative rate of growth. So let's start off with y. What is y? Y would be the final amount. What is the final amount here? That would be 1.32 billion. So it's we're just going to keep it 1.32. That's going to equal, now what did we start with? We started with 1.26 billion. E, which will always be E. Do we know what our k is? No, we don't. Now, tough part here though, what is our time? Started in 2000, finished in 2007, so we have 7 years for our time. Now we want to get e by itself, right? So we divide by 1.26 to get 1.0476. That's going to equal e to the 7k. Now what do we do when we get e all by itself? We have to take the natural log of both sides. So we're taking right now the natural log of both sides. When we do that, this side turns into 0.0465. That's going to be equaling to 7k times ln e. ln e, the natural log of e, turns into 1. So we are left with 0.0465 equaling 7k. We divide by 7, so we get k equals 0.0066 for our rate of growth. Part B asks, when will China's population reach 1.5 billion? So we want to reach 1.5 billion. What do we have to do? We have to set our final destination to 1.5 billion. We do that by going 1.5 equals, and our starting was 1.26 e. And now what is our rate of growth? Our rate of growth is 0.0066, but we now do not know our time t. So we want to get e by itself. So we divide by 1.26 to get 1.1905. That equals to e, and then it's 0.0066 t. What do we do now? We have to take the natural log of both sides with all these fun numbers to take logs of. So it's the natural log of e to the 0.0066t. Now what happens is the natural log of this turns into 0.1744, equaling, now the natural log of e just turns into 1, so we are left with 0.0066t. How do we get t by itself? Divide by 0.0066. So t equals now 26.4. So when will China's population reach 1.5 billion? That's going to happen in 26 years. 26 years, and what time did we start? We started in 2000, so it's year 2026 for our final answer. One more. Now we're asked, India's population in 2007 was 1.3 billion and can be modeled by this guy right here. Determine when India's population will surpass China's. T represents years after 2007, ladies and gentlemen. So, in 2007, first thing we have to note is what was China's population? China's population was 1.32 e to the fun decimals again, 0066 t. So, India's population will be represented by this, so it's going to be 1.13 e to the 0.015 t. That, though, is going to be greater than China's population because it's surpassing, which is 1.32 e to the 0.0066 t. Now what do? Let's take the natural log of both sides. We get the natural log of 1.13 e to the 0.015 t greater than. We take the natural log of China's side. I know it looks like a lot of writing. I'm getting sick of it too. So it's 0.0066 t. What happens now? We have the natural log. How is this e attached to that 1.3? It is attached to multiplication, right? Multiplication in a log means that we can add our logs together. So it's going to be the natural log of 1.3 plus now the natural log of e to the 0.015 t. You can do that to one side, so you can do it to the other side. So we have the natural log of 1.32 plus the natural log of e to the power of 0.066 t. The natural log of 1.13 turns into 0.1222 plus, now we bring down the 0.015 t. The natural log of e just turns into 1, so I'm not even going to put that down, is going to be greater than. The natural log of 1.32 turns into 0.2776 plus 0.0066 t, because the natural log of e turns into 1. Now we just have an inequality that we have to solve. So we have to put together our t's and put together our normal numbers. So I'm going to bring this guy over here. How do you do that? I subtract it, so I have 0.1554 plus 0.00, that's a 0, 66t, and that is going to be greater than 0.015t. Subtract this guy over here on the other side of the inequality to give us 0.0084. T is greater than 0.1554. Solving for t, we finally get a divide by 0.0084, so t is now greater than 18.5. And so now this is 18.5 years, right? What are we going to add that to? We're going to add that to 2007, which is when we started, to get year 2025, which is the year that India will pass China in its population. One more thing I want to show you is the logistic growth model, which is a growth model that represents the growth that has a limiting factor. This is very useful for population. Here is the growth model. T represents times. You will be given your A and B and your C, but we will use this with a graphing calculator because we're going to be asked to graph these kind of problems. But that does it for section 7.8, using exponential and logarithmic functions. Good day.